When you look at any precision made object, like your phone or a part in a jet engine, you're looking at the result of a perfect cut. But behind that perfection, there's a whole unseen science at play. And it's all governed by this powerful but kind of little known standard, ISO 3685. Today, we're diving into that hidden world.
So let me ask you something. Picture a huge, state-of-the-art factory. Robots, machines, everything humming along perfectly, making thousands of parts an hour. What do you think is the one thing that could bring that entire multi-million-dollar operation to a dead stop? A power outage? Maybe a massive software bug?
Well, the answer is actually way, way smaller than you'd think. It's a tiny piece of metal. Yep, a single cutting tool that fails at the absolute worst moment. And believe me, that one tiny failure can cause some seriously massive problems. And this gets to the heart of the issue. When a tool fails unexpectedly, it's not just some small inconvenience. No, it's a full-blown disaster in the manufacturing world. We're talking about incredibly expensive parts getting completely ruined. We're talking hours, sometimes even days of downtime that costs a fortune, and a real hit to quality and safety. So, how in the world do engineers fight back against that kind of chaos? Well, they use a rule book, a common language that lets everyone, no matter where they are, stay on the same page. And that language, that standard, is ISO 3685. It's the international playbook for defining the life of a cutting tool. So what exactly is tool life according to the standard? Well, think of it this way. It's the measured amount of time a tool can do its job right before it gets too worn out to be effective. And the key part here is that worn out isn't just a feeling or a guess. It's a very specific, predefined limit. And that is what allows engineers to make fair, apples-to-apples comparisons between any two tools anywhere on the planet. So how do they actually measure this stuff in the real world? Well, they can be pretty straightforward, just timing how many minutes it's been cutting, or maybe they'll measure the volume of metal it's removed. But to get really scientific, engineers measure the physical wear and tear on the tool itself. They look at something called flank wear, which is kind of like the sole of your shoe wearing down, or they'll check for crater wear, which is where the top surface starts to get hollowed out from all that intense heat and pressure. Okay, so this is where it gets really interesting. Why does a tool wear out? It's not just one thing. Imagine you're in front of a big control dashboard with all these different levers and dials. Engineers have to get that balance just right to squeeze every last second of life out of their tools. And it really all boils down to a handful of key factors. You've got the basic physics of the cut itself, how fast you're going, how deep you're cutting. Then there's the material science part of it, what the tool is made of, what you're trying to cut. And finally, you have the whole environment, everything from coolants and lubricants to machine vibrations and even the super precise shape of the cutting edge.
Now, of all those factors, cutting speed is the absolute heavyweight champion. There's no getting around it. It's a simple, brutal trade-off. The faster you cut, the more heat you generate, and more heat makes the tool material get soft and wear out, exponentially faster. It's this constant battle between trying to be productive and trying to make your tools last.
So how do you possibly fight back against all that intense heat and friction? With some amazing material science, that's how. Modern tool coatings are basically high-tech armor for the cutting edge. We're talking about these ultra-hard ceramic layers, things like titanium aluminum nitride, or even advanced nanocomposites that create this incredible thermal and chemical shield. These coatings can seriously extend a tool's life, even in the absolute toughest conditions. And those tough conditions, they're becoming the new normal. Why? Because the materials we're building things with for aerospace, for medical implants, for high-performance cars are getting crazier and tougher every day. Trying to machine a super alloy like Inconel 718 is like trying to carve a diamond with a butter knife. It puts an unbelievable amount of stress on the tool, which makes managing that tool's life absolutely critical. And all of this brings us to the modern era of manufacturing. We're finally moving away from just reacting, waiting for a tool to break and then fixing it. Now it's all about being predictive. It's using data to know exactly when a tool is about to fail. And sometimes it all comes down to a single number. For a lot of the common tools out there, this is the magic number, 0.3 millimeters. That's the typical amount of flank wear that basically screams, hey, this tool's life is over. Once it hits that tiny limit, it is time for a change. So how do you track that wear down to the millimeter without stopping the machine to look?
You do it with a predictive pipeline. First, you have sensors on the machine that are constantly listening, collecting data on force, vibration, and heat. Second, you have AI models that sift through all that data, and they can spot these tiny little patterns, like a slight change in vibration, that a human would never, ever notice. These are the telltale signs of failure. Third, the system uses those patterns to predict the tool's remaining useful life. And finally, it tells someone to make the change at the absolute perfect moment, not a second too early and definitely not a second too late.
And listen, this isn't science fiction we're talking about. This combination of the ISO 3685 standard and artificial intelligence is what is shaping the smart factory of today and, for sure, the factory of tomorrow. And the results? They speak for themselves. Just look at some of these real-world cases. When you're machining tough titanium alloys, if you combine the right coating with just the right lubrication, boom, tool life goes way up. For stainless steel that just wants to chew up your tools, those nanocomposite coatings we talked about make a massive difference. And you can see that across the board. AI models are proving they can predict wear with incredible accuracy, stopping that million-dollar downtime before it even has a chance to happen. So here's the big takeaway. The future of manufacturing isn't just about making stronger tools. It's about making smarter tools. By bringing together sensors and AI, factories are hitting a level of reliability and productivity that was just, well, impossible before. Which really leaves us with one final thought to chew on. As these systems get smarter and smarter, constantly optimizing every single cut based on live data, who's actually making the decisions? In the factory of the future, is that perfect cut going to be the work of a skilled machinist's intuition, or will it be the cold, hard, perfect logic of an algorithm?